Hi everyone, I'm Bozhidar Stevanoski, and today I'll be presenting our work on automated privacy risk estimation of limited fixed aggregate statistics. This is work done in collaboration with Yifeng and Yves-Alexandre de Montijoye. Releasing aggregate statistics is one of the most popular ways of sharing data. Consider a data curator holding a private tabular dataset D, for example, a dataset about employees at Imperial College London. And rather than sharing record-level data, the curator selects a set of aggregate statistics and shares only these fixed aggregates. For example, the curator might share aggregates about the number of employees in the departments of physics with a salary larger than £50,000, which might be, say, 120, and number of 30-year-old male employees in the department of computing, which might be, say, 5. So can an adversary, with access to only limited number of released aggregates, infer sensitive information about the users in the dataset? Well, there is a large body of work on empirical inference attacks against other data releases, such as machine learning models and synthetic data releases. We currently lack comparable methods for evaluating the privacy risk of fixed aggregates, especially when only limited number of aggregates are released. But can releasing only a limited number of fixed aggregates even put users at risk of inference attacks? Well, yes. Sometimes the inference can even be deterministic with complete certainty. Consider a 30-year-old male employee working in the department of computing as our target user. And suppose the curator has released a limited number of aggregates, among which are these two, that there are 5 30-year-old male employees in the computing department and 5 30-year-old male employees in the computing department with a salary smaller than £50,000. So taken individually, these two aggregates appear safe. However, taken together, they reveal the salary attribute of our target user. Because both aggregates equal 5, everyone in that group of 5 earns below £50,000, and our target is one of them. So no other value is even possible, and we can infer the target user's salary with 100% certainty. The literature and attacks against fixed aggregate statistics has largely focused on reconstruction attacks. Reconstruction attacks aim to reconstruct the private dataset D by searching for a dataset whose values in the released aggregates match or closely follow the released aggregates in D. As of today, there are two state-of-the-art reconstruction attacks against fixed aggregate statistics. About it all proposed an attack which we refer to as CAP that aims to find the tentative reconstructed dataset by formulating a constrained integer programming task. Digital proposed an attack which we refer to as RAP that uses a synthetic data generator model trained on the released aggregate statistics. We adapt these attacks to a task of attribute inference by first generating k tentative reconstructed datasets and then taking a majority vote of the target user's sensitive attribute from all k datasets. In this paper, we propose DISIA, our method for attribute inference attacks against fixed aggregate statistics from a tabular data. It consists of two modules, a deterministic and a stochastic module. The deterministic module deterministically verifies if one and only one value for the sensitive attribute of the target user is deterministically feasible, given the released aggregate statistics, and outputs that value. It consists of two steps, both relying on running a constrained integer programming task to first find a feasible value for the target user sensitive attribute, and second, verify whether this is the only feasible value. To do so, we add a constraint that explicitly excludes this value. If the constrained integer program finds no alternative feasible value, we infer the target's sensitive attribute with certainty. Otherwise, we use the stochastic module. So if more than one value is feasible, the stochastic module estimates the likelihood of each and outputs the most likely one. It consists of three steps. First, it samples records at uniform random from an auxiliary dataset to create the so-called shadow datasets. Then it evaluates the aggregates on these shadow datasets And finally, it trains a machine learning model to predict the sensitive attribute of the target user. So how well does DZIA work? We instantiate DZIA and the reconstruction-based attacks on the US Census PPMF data. We show DZIA to reach an AUC of 0.75, while the best reconstruction-based method gets an AUC of 0.64. We also compare the performance of the methods focusing on the most vulnerable users. Shown at the inset, DZIA outperforms the reconstruction-based methods. At a false positive rate of 10 to the power of -3, DZIA achieves a true positive rate of 0.14. So DZIA successfully identifies highly vulnerable users even when only a small number of aggregates are released, identifying risks that state-of-the-art reconstruction-based attacks miss. Recall that DZIA relies on an auxiliary dataset. However, a real-world auxiliary dataset might not always be available for the attacker, despite being commonly accepted as a realistic assumption in the literature. So here, we relax this assumption by replacing the auxiliary dataset with synthetic data generating from the released aggregates. DZIA's performance degrades minimally under this substitution. The AUC decreases from 0.75 to 0.72, and the true positive rate at a false positive rate of 10 to the power of -3 decreases from 0.14 to 0.10. Importantly, DZIA with synthetic auxiliary data achieves a higher AUC than other state-of-the-art methods, including those with real-world auxiliary data access. Next, we investigate the performance of DZIA and the reconstruction-based methods across different release sizes and noise levels. We vary how many aggregates are released from 1 per 16 users up to 1 per user on average. DZIA outperforms the reconstruction-based attacks across the whole range, and as expected, increasing the number of released aggregates increases the risk and leaves the performance of all methods. Similarly, DZIA outperforms reconstruction-based methods across noise levels and is the only method that keeps a non-zero true positive rate at a low false positive rate. Finally, we extend DZIA to a membership inference stack with small modifications on both the deterministic and the stochastic modules. In the deterministic module, instead of verifying the sensitive attribute value, we verify membership. We check whether the target's presence or absence is the only feasible option under the released aggregate. In the stochastic module, similarly, we train the machine learning model to estimate the likelihood of membership. We create the shadow datasets such that for each shadow dataset, a coin toss decides whether the target user's record is included or not, and then we train a machine learning model on these datasets to predict the target user's membership. Our results show that DZIA performs well, both overall with an AUC of 0.75 and on the most vulnerable target users, outperforming RAP, while a straightforward adaptation of CAP does not perform better than a random guess. To conclude, we propose DZIA, a method for automatically evaluating attribute inference risk of limited fixed aggregate statistics. We show DZIA to be highly effective at identifying vulnerable users that reconstruction-based attacks miss, even without access to real-world auxiliary data. Overall, our results show that even a limited number of aggregate statistics can reveal sufficient information to expose users to risk from inference attacks, leaving some users disproportionately vulnerable, and emphasizing the need for formal privacy mechanisms and empirical testing before the aggregates are released. We release our source code on GitHub, which is available through the QR code on this slide. Thanks so much for your attention, and if you have any questions, please don't hesitate to reach out to us. Thanks so much.